Earth's magnetic field is invisible. You cannot see it. You cannot feel it. And yet it surrounds our planet like a giant shield extending tens of thousands of kilometers into space. It deflects charged particles from the sun, protects our atmosphere, and quietly makes modern civilization possible. But what if that shield suddenly disappeared? What if Earth lost its magnetic field entirely? The magnetic field is generated deep inside our planet, in the outer core, where molten iron moves in powerful currents. This motion creates a geodynamo effect, producing a global magnetic field that stretches outward into space. This protective bubble, called the magnetosphere, acts as Earth's first line of defense against solar radiation and cosmic particles. Without it, the solar wind would directly strike the atmosphere. At first, nothing dramatic would happen that you could see with your eyes. The sky would look the same. Gravity would not change. The air would still be breathable. But above the surface, the environment would begin to transform immediately. Charged particles from the sun would start penetrating deeper into the upper atmosphere. Satellites in orbit would be exposed to far higher radiation levels. Many of them would fail within days or weeks. GPS systems would become unreliable. Communication networks that rely on satellites could collapse. Astronauts aboard space stations would face extreme radiation exposure, forcing emergency evacuations. On the ground, the effects would be slower but increasingly serious. The ozone layer, which protects life from harmful ultraviolet radiation, could begin to degrade under constant bombardment from energetic particles. Increased UV radiation would reach the surface, raising risks of skin cancer and damaging plant life. Power grids would be at severe risk. Solar storms already pose threats during strong geomagnetic events. Without a magnetic field, those events would become far more intense. Induced electrical currents could overload transformers, causing widespread and prolonged blackouts. Modern civilization depends on stable electricity. Hospitals, water treatment plants, financial systems, internet infrastructure all rely on continuous power. A major global grid failure could trigger cascading economic and humanitarian crises. Air travel will be affected as well. Aircraft flying at high altitudes are already exposed to slightly higher radiation levels. Without magnetic shielding, radiation exposure during flights would increase significantly, especially near the poles. Many flight routes might need to be permanently altered, but perhaps the most profound long-term effect would involve Earth's atmosphere itself. Mars provides a cautionary example. Billions of years ago, Mars had a magnetic field. When its core cooled and the magnetic field faded, solar wind gradually stripped away much of its atmosphere. Today, Mars is thin, dry, and cold. If Earth lost its magnetic field, atmospheric loss would begin, but much more slowly than on Mars. Earth's stronger gravity would help retain most of the atmosphere for a long time. This would not be an overnight transformation into a barren world. It would be a gradual weakening of protection over thousands or millions of years. Life would not vanish immediately. Humans have survived magnetic reversals before. Geological records show that Earth's magnetic field has flipped many times in the past. During reversals, the field weakens temporarily, yet life continued. However, a complete and permanent collapse would be different from a temporary reversal. Over long timescales, radiation exposure would increase mutation rates. Some organisms might adapt, others might decline. Surface life would face new environmental stress. The most vulnerable species would struggle first. As radiation levels increased, technological society would need to adapt quickly. Underground infrastructure would become more common. Critical facilities such as data centers and power stations might require heavy shielding. Space travel will become dramatically more dangerous. Missions beyond Earth's atmosphere will require stronger radiation protection. Permanent human presence in orbit could become extremely difficult. Agriculture would face new pressures. Increased UV radiation could damage crops and reduce yields. Protective greenhouse systems might become necessary in many regions. Certain ecosystems, particularly marine plankton that depend on stable light conditions, could be disrupted. Since plankton form the base of the ocean food chain, even small changes could ripple through entire marine ecosystems. Animal migration patterns might shift as well. Some species rely on Earth's magnetic field for navigation. Birds, sea turtles, and certain marine animals use magnetic cues to travel long distances. Without a stable magnetic reference, migration routes could become chaotic, affecting reproduction and survival. Human health would require additional protection strategies. Increased radiation exposure raises cancer risk. Protective clothing, building materials, and possibly even pharmaceutical countermeasures will become part of everyday life. Over generations, natural selection might begin to favor traits that tolerate higher radiation levels. But evolution works slowly compared to technological change. The economic consequences would be enormous. Satellite-dependent industries would need to reinvent themselves. Telecommunications might rely more heavily on ground-based infrastructure. The cost of maintaining space assets would increase significantly. Insurance markets would adjust to new environmental risks. Governments would invest heavily in monitoring solar activity and atmospheric chemistry. Despite these challenges, humanity would not necessarily go extinct. Earth's atmosphere would not vanish overnight. Oceans would remain. Gravity would still hold everything in place. The sun would continue to shine. The magnetic field is crucial, but it is not the only thing keeping Earth habitable. Over very long time scales, however, the cumulative effects could reshape the planet. If atmospheric erosion gradually intensified, surface temperatures might shift. Climate systems could change in subtle but significant ways. Radiation-resistant organisms might dominate certain ecosystems. The biosphere would evolve under new pressures. The deeper question is whether Earth's magnetic field could truly disappear permanently. Current understanding suggests that as long as the outer core remains molten and convective, the geodynamo will continue operating. The core is expected to remain active for billions of years. A sudden permanent loss is extremely unlikely in the near future. Magnetic reversals, on the other hand, are inevitable. They have occurred many times before and will occur again. During a reversal, the field weakens but does not vanish entirely. Civilization may one day experience such a transition. If so, technological systems will need to be more resilient than ever before. The invisible shield surrounding Earth is easy to forget because it works silently. It does not make headlines. It does not appear in the sky as a wall or barrier. Yet without it, modern civilization would face enormous challenges. The magnetic field reminds us that habitability is not defined by distance from the sun alone. It depends on complex planetary systems operating deep beneath our feet. Earth is not just a rock in space. It is a dynamic machine powered by internal heat, generating forces we rarely consider. And among those forces is a magnetic shield that quietly protects every living thing on the surface. If that shield were gone, life would not instantly end, but the world we know would change in ways both subtle and profound.